Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine for a moment that the universe is this massive, complex symphony, but we've only ever listened to it through a tiny, cheap AM radio speaker.
Right.
You get the melody, maybe, but you're missing 99% of the instruments, the texture, the depth. Now imagine someone hands you this full, high-definition digital receiver, and it's capable of isolating 102 distinct frequency channels, most of which we've, never even heard before.
That is absolutely the right analogy.
That sudden explosion of information.
Right.
That's the perspective shift we're deep diving into today. We are talking about NASA's monumental achievement with the SPHEREx telescope, which has just given us a completely new way of seeing the cosmos.
It really is. The sources we've pulled together all center on this massive milestone announced by NASA. And this isn't just some incremental improvement on, existing views of the universe.
No.
This is a wholesale systemic revolution in how we capture the entire sky. It forces us to redefine what an all-sky map even means.
Okay, let's unpack this. The big news is that SPHEREx, and that stands for Spectrophotometer for the History of the Universe, Epoch of Reionization, and ICE's Explorer.
Which is a mouthful.
It is, but we absolutely have to explain why every part of that name is so critical. The news is that it has successfully completed its first full sky infrared map.
Right.
And it did this by capturing the entire cosmos in an unprecedented 102 distinct bands of infrared light.
Exactly. So our mission today is to extract the most critical insights from this. I mean, it's an astronomical achievement in every sense of the word.
Yeah.
We need to look at the tech, how they actually built a system capable of this.
The mechanics of it.
And then, crucially, how this multi-channel high-resolution spectral atlas is specifically designed to answer some of the most fundamental lingering questions we have about the universe's origin, its rapid early expansion, and, well, its evolution over 14 billion years.
And I want to emphasize the value for you, the learner. This is not just an announcement of a pretty picture. This is NASA saying, we have created 102 completely unique data fields, 102 separate maps of the entire cosmos, all at the same time.
It's staggering.
And each map is packed with information that was previously either too faint, too obscured, or was just hidden in a wavelength we weren't even monitoring. So this deep dive will reveal what those data streams are designed to tell us. From the universe's absolute infancy, tracing those fundamental ripples from the moment of inflation all the way to locating the molecular ingredients for life in our own Milky Way galaxy. It's a fantastic, in-depth shortcut to understanding one of the most powerful tools in modern astrophysics.
Let's start with the core accomplishment then, the mapping of the entire sky in infrared light. It sounds simple when you say it like that, but the scope is just enormous, and the choice of infrared is really the linchpin of the whole mission.
And crucially, this is energy the human eye can't detect, right? Infrared light, we often think of it as heat radiation, and it's absolutely everywhere in the cosmos.
Prevalent, yeah.
It's the light from cooler objects like dust and certain molecules. And it's also the light from the most distant objects, stretched by the universe's expansion. If you're only looking in visible light, you're missing most of the action, and you're often blocked completely by cosmic dust.
The ability of infrared light to pierce through those dense, dusty nebulae it's paramount here. Stars and planets are born in these huge clouds of gas and dust. They're like opaque curtains in the visible spectrum.
You can't see a thing.
Not a thing. But infrared light, with its longer wavelengths, it just slips right through that curtain. It allows us to see the actual heat, the molecular signatures of the stellar nurseries within. SPHEREx isn't trying to find new visible light objects. It's trying to see the objects that are defined by their invisibility.
And the timeline for this mission's initial phase is just incredibly tight.
It is. So the SPHEREx mission launched in March 2025 and began systematic sky mapping by May.
Just a couple months.
Barely. And by December 18th, 2025, so just about 6 months after the sensors turned on, it completed its first all-sky mosaic.
6 months.
In just half a year, it viewed space in every single direction, capturing 360 degrees of the celestial sphere.
A 6-month turnaround for a map of the entire universe. Especially one with that much complex spectral data that sounds almost impossibly fast. It makes me wonder, how robust can a single 6-month scan really be? Are we talking about high-quality final data right out of the gate?
That's a critical question, and the answer is that this first mosaic is really just the foundation. The sources confirm that SPHEREx is designed as a marathon, a systematic survey that requires repetition. Its primary mission is set for 2 years.
2 years.
And during that time, it will complete 3 additional all-sky scans, so it's going to view the entire sky 4 times over 2 years.
So it's not just one 102-channel map, but 4 overlapping maps of the entire sky, all layered on top of each other. Why? Why is that layering necessary? What does that buy them scientifically?
Precisely. Merging those 4 maps together is fundamentally about increasing the signal-to-noise ratio.
Okay.
Think of it like taking 4 long exposures with a camera instead of 1 short one. Each time SPHEREx scans a region, it collects more photons, more information. By co-adding the data from all 4 passes, they can significantly increase the sensitivity of the measurements. It lets them detect fainter, more distant objects with much greater confidence and filter out, transient noise like cosmic rays hitting the detector.
That systematic repetition for complete scans,
Yeah.
that must be absolutely essential for the mission's cosmological goals, especially when you're trying to measure these tiny, subtle differences in how galaxies are clustered billions of light years away.
Absolutely. And here's a crucial detail that really aligns with the collaborative ethos of modern space science.
What's that?
The entire data set, all 4 scans, all the co-added final maps, all the raw spectral information is being made freely available to scientists and to the public.
Wow.
This completely democratizes the discovery process globally. It ensures that every research institution, regardless of its size, can dig into the deepest mysteries of the universe.
That public access feature seems critical. What's the precedent for releasing such a massive spectral data set so quickly? Is that typical for a mission of this scale?
It's becoming the gold standard, particularly for survey missions like this. The sheer vastness of the data, spanning 102 unique channels across the entire sky. No single team could ever exploit its full scientific potential on their own.
Just too much.
Exactly. By making it immediately public, NASA ensures that thousands of independent researchers, from planetary scientists to cosmologists, can apply their specific expertise to different subsets of the data all at the same time. It just accelerates discovery exponentially.
But let's go back to those 102 spectral channels. For a non-astrophysicist, it's still a bit abstract. I find it hard to picture what having 102 specific measurements of invisible light actually means in practice. What information is being separated by these distinct wavelengths? Well, the number 102 is a technological and scientific sweet spot. It's a compromise between survey speed, scanning the whole sky quickly, and spectral resolution, getting enough detail to identify materials and measure distances. The source material gives us some really concrete examples. Okay, give us an example of this separation in action.
All right. Consider a star-forming region. In one set of, say, 10 spectral channels, the emissions might be completely dominated by the light from hot, massive young stars.
Okay.
That data would show up as these bright, energetic points, maybe looking blue or white if we assign them visible colors. But shift your focus just slightly to a different set of channels centered around, say, 4 to 8 microns in the infrared, and suddenly you see something completely different.
You lose the stars and you gain the dust, right?
Right. Precisely. You gain the thermal radiation that's emitted by the cosmic dust grains that have been heated up by those very stars. Cosmic dust, like you said, is critical for forming new stars and planets, but it's the ultimate obscure, invisible light.
Right.
SPHEREx captures this dust brilliantly because it radiates so strongly in specific infrared bands. And conversely, the source mentions that this same dust is totally invisible in others.
So you have one map where a massive star-forming nebula is a glowing beacon of heat, and then you have a complementary map where that same nebula just disappears entirely, leaving only the background stars.
Exactly.
The scientific breakthrough isn't just the map itself, it's the comparison and synthesis of all 102 of those maps.
That's it. Each channel acts as a targeted filter. It's picking up the unique emission signatures, the fingerprints of specific atoms or ions or cold molecules. Comparing the intensity across those 102 channels lets astronomers figure out not only what is present,
like carbon monoxide, water ice, hot hydrogen.
Exactly. But also how distant it is and how much of it there is.
This is where it gets really interesting, because this mission's unique ability to combine this massive scale with such a wide, rich spectrum earned it this fantastic, memorable nickname.
Ah, yes. The comparison to the ultimate eye in the animal kingdom.
Yes.
Beth Fabinski, the SPHEREx project manager at JPL, she called it the mantis shrimp of telescopes.
That is instantly memorable, and it's such a high bar. For those who don't know, the mantis shrimp is famous for having one of the most complex visual systems in nature. It can see up to 16 different types of photoreceptors.
Compared to R3.
Exactly. It sees channels for ultraviolet light, polarized light, stuff that's way beyond what we can perceive.
And the analogy holds up perfectly for SPHEREx's function. The telescope's real power is that it combines this amazing multicolor detection system, the 102 spectral channels, with the ability to survey a massive wide swath of its surroundings, the entire sky.
And to do it over and over again quickly.
That's the key. It's not just seeing many colors in one tiny spot like GWST does. It's seeing everything in 102 colors every 6 months. It's the ultimate cosmic spectral survey machine.
The mantis shrimp is a brilliant analogy for the result, the richness of the data. But let's shift our deep dive into the engineering behind the how. How does a telescope manage to generate 102 separate spectral maps at the same time, with this kind of speed and coverage?
This brings us to the core scientific technique driving the mission, spectroscopy. At its heart, spectroscopy is just the process of separating the light from a source into its component wavelengths.
Into its colors.
Into its colors, exactly. So when SPHEREx says it detects 102 spectral bands, it means it is precisely measuring the intensity of light at 102 specific, narrowly defined points all across the infrared spectrum.
So it's not just painting a general infrared picture, it's quantitatively measuring the specific fingerprints of light emitted by different atoms and molecules out there. It's doing chemistry on a cosmic scale?
That's precisely right. Every element, every common molecule, hydrogen, oxygen, carbon dioxide, and every physical process in the universe, from the extremely hot glow of a quasar to the cold, complex organic molecules hidden in dust clouds, has a unique spectral signature. By sampling 102 points across that spectrum, SPHEREx acquires a detailed yet wide-ranging picture of what's there and what state it's in.
That still sounds like a massive technical challenge. How did the engineers manage to create a system that can look at the whole sky and filter it into 102 separate data streams, all while staying cold enough to even function in the infrared?
It is a technical marvel, and it required overcoming some significant thermal challenges. Since SPHEREx is looking for infrared light, which is essentially heat, the detectors themselves have to be kept incredibly cold, many degrees below zero, to prevent their own thermal radiation from drowning out the faint cosmic signal.
Right, it would just be noise.
Total noise. But the real innovation is in the filtering mechanism.
Let's detail that. How did they physically achieve the 102 channels?
So, to get this massive color spectrum simultaneously across its wide field of view, the observatory uses 6 individual detectors. And here is the clever bit of optical engineering. Each of those 6 detectors is paired with a specially designed filter called a linear variable filter, or LVF.
A linear variable filter. Okay, explain that in concrete terms. What does a gradient filter look like?
Picture a standard camera filter, which usually just blocks all light except for one specific color.
Okay.
The SPHEREx filter is different. Imagine a narrow rectangle of glass where the color it transmits changes continuously along its length, kind of like a smooth rainbow or a gradient. At one end, it might only let through light at 1 micron, which is near infrared. Halfway down, it might let through 3 microns, which is mid-infrared. And at the far end, 5 microns.
So the filter's properties actually change depending on where the light hits it.
Exactly. As the light from the sky passes through the telescope and hits the detector, the light falling on different physical locations of that detector is simultaneously measuring a different wavelength. The light that hits the left side of the detector is filtered differently than the light that hits the right side. This gradient allows each detector to simultaneously measure 17 distinct colors or wavelength bands.
That makes the math very clear, but incredibly efficient. 6 detectors times 17 distinct simultaneous spectral bands per detector gives you the grand total of 102.
That's it.
So every time SPHEREx takes a snapshot of a tiny patch of sky, it's actually generating 102 separate measurements of spectral intensity for that one patch.
Correct. Every all-sky map SPHEREx produces isn't just one file. It's 102 separate, highly precise maps, each one telling a different, unique story about the structure and content of the universe at a different spectral depth. And this high sampling rate, 102 channels, is what sets it so far apart from its predecessors, which might have used only 3 or 4 broadbands.
Okay, now let's talk logistics. How does this system, this cosmic barcode scanner, manage to systematically cover the entire sky so quickly and precisely?
It all relies on a very carefully maintained orbit and a systematic scanning pattern. SPHEREx is orbiting Earth in what's called a polar orbit. It travels from north to south, passing over the poles about 14.5 times every day.
Right.
And during those orbits, it points its gaze slightly away from the Earth and the sun, and it captures a specific narrow strip of the sky.
So I'm picturing it essentially painting a long, circular swath of the sky with every single orbit.
That's a perfect way to put it. Each day, it captures about 3,600 individual images along one of these circular strips.
Right.
But here's the key to getting full coverage. Because the Earth is also moving around the sun, the telescope's line of sight gradually shifts relative to the distant stars. The strip of sky it views on day 1 is slightly different from the strip it views on day 10 or day 90.
That gradual systematic shift must eventually guarantee a full sweep.
It does. After 6 months of continuous, systematic scanning along these slightly shifting strips, this gradual progression allows the observatory to view space in every direction. It captures the entire 360 degrees of the sky.
And then it just starts over.
And then as the orbital geometry repeats itself, it starts over again for the second scan, ensuring they collect those 4 repeated exposures we talked about.
That repetitive, systematic coverage is what guarantees that sensitivity boost. But let's talk about the real revolutionary leap this detailed spectral data enables. The jump from a 2-dimensional map of the cosmos to a complete 3D atlas.
This is perhaps the most critical scientific application of those 102 spectral bands. Other powerful observatories have been mapping the positions of galaxies for years, but generally those maps are 2-dimensional. We know where they are in the sky, their celestial coordinates, but we don't know precisely how far away they are. They're just flattened onto a sphere.
So if I see 2 galaxies that look like they're right next to each other on the map, I have no idea if they're actually cosmic neighbors, or if one is 10 billion light years behind the other, just lined up by chance in our field of view.
Exactly. That missing depth is the distance component, and SPHEREx's 102-channel multi-wavelength view provides the solution through what's called cosmological redshift.
Okay, let's elaborate on this, because this is where the precision of those 102 channels really proves its value. How does measuring 102 points across the infrared spectrum give them the distance?
Well, when a galaxy emits light, that light has specific, recognizable spectral features, emission lines, and absorption lines created by the elements within it.
Okay, like a fingerprint.
A perfect fingerprint. But because the universe is expanding, the farther away a galaxy is, the faster it appears to be moving away from us. This rapid motion stretches the light waves, shifting those recognizable spectral features towards the red or infrared end of the spectrum. This is redshift.
So the farther away the galaxy, the more the light is stretched, and the deeper into the infrared SPHEREx we'll see those fingerprint features.
Precisely. Now, the older, simpler infrared surveys like WISE used only 4 broad channels. That's enough to guess the redshift, but it's often prone to errors, especially when you're trying to pin down the distance to hundreds of millions of objects.
So it's more of an estimate.
A very rough one, yes. SPHEREx, by measuring 102 specific points, allows astronomers to do much more accurate spectral curve fitting. They can map the precise shape of the spectral curve of that galaxy's light.
That ability to measure the curve with high resolution, the 102 photometric bands, must allow them to pin down the distance with far greater certainty than before.
It does. They can identify specific spectral breaks and molecular features and then measure exactly how far they've been redshifted. This allows them to determine the distance to hundreds of millions of galaxies, converting that 2D celestial map into a full 3D map of the universe. It provides accurate depth and volume. And that 3D distribution, how galaxies are clustered and distributed across billions of cubic light years, that holds the key to unlocking the deepest mysteries of the universe's past.
That transition to the high-fidelity 3D map really sets the stage for the enormous scientific goals of this mission. When you look at the name again, Spectrophotometer for the History of the Universe, Epoch of Reionization, and ICE's Explorer, it's clear this telescope is targeting cosmic history across the entire age of the cosmos. So let's tackle the most dramatic one first.
We have to start with the most distant and complex target, which is literally at the very, very beginning of time.
Goal number 1. Gaining insights into the epoch of cosmic inflation.
This is the cosmological reason they need that 3D map of hundreds of millions of galaxies. Inflation is a theory describing an extraordinarily rapid and massive expansion of the universe in the earliest moments of existence.
And the timing is just mind-bendingly short.
It's almost incomprehensible. The sources detail the timing of this event. It occurred in the first billionth of a trillionth of a second after the Big Bang.
A fraction of a fraction of a fraction of a second.
Yeah.
And yet it determined everything we see today.
During that infinitesimally brief moment, the universe expanded by a factor of a trillion-fold. This dramatic burst solved several long-standing cosmological puzzles, but the evidence for it is incredibly difficult to find because it happened so quickly and so early.
So if this event was so fast and happened so long ago, how can a telescope launched in 2025 possibly find the evidence for it billions of years later? What's the link between SPHEREx's 3D map and that moment of inflation?
The link is quantum mechanics and gravity. According to inflation theory, the universe was not perfectly uniform before, during, or after that rapid expansion. The quantum fluctuations, these tiny random variations in energy density that existed at the subatomic level, they were stretched out to cosmic scales during that trillion-fold expansion.
So the tiny random jitters that are inherent in quantum mechanics became massive, observable ripples across the structure of the brand new universe.
Precisely. These initial microscopic variations in density were stretched out, and they became the seeds for all the large-scale structure we observe today. Over the next 14 billion years, gravity acted on these slightly denser regions, causing them to collapse and form the massive clusters and superclusters of galaxies we're now mapping.
So the current 3D distribution of galaxies is like a fossil field of those initial quantum ripples.
That's the perfect term for it.
Ah, I see the connection now. By creating a precise 3D map of how those hundreds of millions of galaxies are distributed and clustered today, scientists can effectively reverse engineer the size and shape of those initial density ripples that were set during inflation. They're looking for subtle statistical patterns in the galaxy distribution.
Exactly. The subtle variations in galaxy clustering today are the imprint of that brief, explosive moment. SPHEREx is looking for two specific signatures. Evidence of something called non-Gaussianity, meaning the distribution of the ripples wasn't perfectly random, and clues about the physics of the energy field that actually powered inflation. Measuring these variations with the precision afforded by a 3D map of this size is one of the mission's absolute highest priority goals. It's trying to help us understand the specific physics of how the universe began.
That is truly tackling the biggest possible question. Okay, let's fast forward from that microsecond event to goal number 2. Tracing the intermediate history of the cosmos, specifically galaxy evolution over 14 billion years.
This goal leverages the full spectral depth of the 102 channels to understand how galaxies have lived and died across the universe's history. Galaxies aren't static islers. They're dynamic, chaotic systems that are constantly merging, consuming gas, generating new stars, or, shutting down their star formation process entirely.
And the 102 spectral maps allow scientists to trace this history in a way that the handful of colors available to older instruments simply couldn't.
Yes, because different spectral channels are sensitive to different cosmic phenomena. For example, some channels are dominated by the light of young, hot, massive stars. Other channels might be more sensitive to the older, redder stellar populations. By measuring the relative intensity across all 102 bands, astronomers can accurately reconstruct the star formation history of a galaxy at any point in time.
So they can look at a distant galaxy, measure its 102 spectral fingerprints, and determine not only its distance, but also whether it's currently a starburst galaxy furiously generating new stars, or a quenched galaxy that's run out of gas and is basically dormant.
That's the key power. They can trace phenomena like metallicity, the amount of heavy elements present, which is an indicator of how many generations of stars have already lived and died within that galaxy. The 102 bands allowed them to build a complete time-sequenced inventory of how galactic structures have evolved.
Distinguishing between changes caused by, say, just running out of gas versus changes from violent galactic mergers.
Right. This provides the context for everything we see locally, including our own Milky Way.
That's a staggering amount of data focused on the distant past and present. But let's bring the focus much closer home for goal number 3, the ingredients for life.
This is where the ICES Explorer part of the SPHEREx acronym comes into play. It's focusing on the chemical precursors for life, which are distributed across the dense, cold molecular clouds of our own Milky Way galaxy.
So we move from mapping the distribution of hundreds of millions of galaxies across 14 billion years of history right back to the dense dust clouds in our own arm of the spiral. That's a massive shift in scale.
It is, but it uses the exact same technology, spectroscopy, just applied to different objects. This goal ties directly back to what we were saying earlier about specific infrared wavelengths penetrating dust. The source materials stress that these dense clouds of dust where stars and planets form radiate brightly in very specific infrared wavelengths.
Right, if you look at those dust clouds in visible light, they're just black silhouettes. They block all the light from behind. They're cold and dark.
Correct. But if you look at them in SPHEREx's specific infrared channels, you're seeing the thermal heat signature of the dust itself and the unique spectral fingerprints of the molecules, the ices contained within those clouds. When atoms bond together to form molecules, like water or carbon dioxide, they vibrate at unique frequencies.
And those unique frequencies fall into the infrared spectrum.
Precisely. The 102 channels are strategically positioned to detect the vibrational and rotational wobbles of these crucial molecules, especially those that are frozen onto the surface of dust grains in the cold, dark recesses of molecular clouds. They're specifically targeting things like water ice, solid carbon monoxide, carbon dioxide, and methane, alongside more complex organic molecules.
Why is mapping and the distribution of these specific ices so vital?
Because these are the chemical precursors that eventually coalesce into the protoplanetary disks, comets, and asteroids that seed new solar systems. Understanding the abundance and precise distribution of water ice, for example, tells us a great deal about the environment in which planets are born. If a region of the galaxy is rich in water and organic molecules, it's arguably a much better nursery for potentially habitable planetary systems.
So by mapping the distribution and composition of these ingredients for life throughout the Milky Way, SPHEREx helps us understand not just if life is possible elsewhere, but where the best nurseries are located, and what feedstock those new planetary systems had to start with. It's connecting the cosmological history to the biological possibility, all using the same 102 spectral keys.
To truly appreciate the necessity and the scale of SPHEREx's achievement, we really need to place it in context alongside other major missions, both historical and cutting edge. SPHEREx didn't invent infrared sky mapping after all, but it absolutely took the technique to an entirely new level.
So let's start with the history. How does SPHEREx stack up against its infrared predecessors?
We can look at previous all-sky surveys, most notably NASA's Wide Field Infrared Survey Explorer, or WISE. WISE was a hugely successful mission that also mapped the entire sky in infrared light. It performed a crucial census of the local and distant universe.
But where did WISE fall short? What was the thing that necessitated SPHEREx?
The key differentiator, as the source material makes very clear, is the spectral depth, the number of channels. WISE used only 4 broad spectral bands.
Only 4.
4. Imagine listening to that 102-piece symphony through only 4 speakers. You get the volume, sure, but you lose all the detail you need to distinguish a tuba from a trombone. Or, in space terms, a dusty galaxy from a distant quasar. SPHEREx, with its 102 photometric bands, provides far, far greater precision.
So WISE was the initial low-resolution sketch, maybe in 4 colors, and SPHEREx is the final high-definition spectral atlas with 102 distinct shades.
Exactly. The sheer volume of spectral data, the detail provided by those 102 different measurement points, is what transforms the map from a broad census into a precise diagnostic tool. As we discussed, that detail is necessary for accurate redshift measurement, which is the whole foundation of the 3D map. The precision of the 102 channels minimizes the ambiguity that plagued distance measurements derived from only 4 broad bands.
Okay, now let's move to the other end of the spectrum and compare SPHEREx to the current rock star of astrophysics, the James Webb Space Telescope, JWST.
Right.
JWST is legendary for its infrared capabilities and depth. If JWST is so powerful, why did NASA decide the single biggest priority was another all-sky survey like SPHEREx?
That's a fantastic critical question, and the answer lies in their fundamentally complementary design philosophies. The sources provide a very clear distinction. JWST can perform spectroscopy with significantly more wavelengths of light than SPHEREx. It has a much higher spectral resolution.
So more detail.
Much more. Where SPHEREx measures 102 distinct points, JWST might measure thousands of points across a narrower spectral range. It allows for incredibly fine identification of molecules and precise velocities.
So JWST is the equivalent of a forensic lab microscope, capable of identifying every single trace element in a sample.
Precisely, but the trade-off is its field of view. The field of view for JWST is thousands of times smaller than SPHEREx's. JWST is designed to peer at one incredibly small, faint target for dozens, even hundreds of hours to gather maximum detail. It is the deep focus magnifying glass. If JWST were to try to map the entire sky, it would take centuries.
Which makes SPHEREx the necessary ultra-wide-angle survey camera. It may not get the forensic detail of JWST, but its unique power comes from that combination of seeing 102 spectral channels and having a massive field of view that covers the entire sky, and doing it 4 times over.
That combination is what allows the cosmological survey, the 3D mapping of hundreds of millions of galaxies. That's something JWST simply couldn't achieve due to its narrow focus and time constraints. SPHEREx provides the universal context. It finds the millions of needles in the cosmic haystack that are worthy of follow-up.
So it's a spotter.
It's the ultimate spotter. It provides the initial distance and classification for targets that JWST or ground-based observatories can then be guided to for deeper, higher-resolution inspection. They are a scientific tag team.
That synergy and complementary role are vital for the mission's broader impact. It's something NASA officials were quick to stress, acknowledging that no single telescope can solve all of astrophysics questions.
Yeah, Sean Donegal-Goldman, the director of the Astrophysics Division at NASA headquarters, noted that the information will be especially valuable when used alongside our other missions data to better understand our universe. This is the definition of multi-mission synergy. The whole is greater than the sum of its parts.
He also perfectly captured the scale of the data delivery when he emphasized, and I'm quoting here, "We essentially have 102 new maps of the entire sky, each one at a different wavelength and containing unique information about the objects it sees."
That just highlights that this is not one discovery, but 102 simultaneous data atlases being handed to the global scientific community.
Exactly.
And the expectation is that this treasure trove of public data will benefit everyone well beyond the initial mission goals. He expressed confidence that every astronomer is going to find something of value here, helping the world answer fundamental questions about the universe's start and the eventual creation of a home for us.
It's a massive public data release. It means that the mission's primary goals, inflation, galaxy evolution, ices, that's only going to be the beginning of the discoveries SPHEREx enables.
Right, which really underscores the point made by JPL director Dave Gallagher. He highlighted the mission as a phenomenal example of a mid-sized astrophysics mission delivering big science.
It's proof that powerful, focused survey missions, when they're designed cleverly, like combining under and two high-resolution spectral channels with systematic full-sky coverage, can unlock enormous potential for discovery and accelerate our understanding faster than just relying on a single megatelescope alone.
The mantis shrimp, it turns out, is the essential key to unlocking the universal spectral atlas.
And what's interesting is how this blend of speed and spectral resolution addresses these fundamental unknowns. It's giving us context for the entire structure of the universe, and it's simultaneously informing cosmology and planetary science. The 3D map links the earliest moments of existence with the very molecules that might form life right here in our backyard. It's a truly comprehensive scope.
Well, the ability to cross-reference data points is unparalleled. Imagine identifying a dense cloud of carbon dioxide ice in the Milky Way, knowing its precise spectral signature from one set of SPHEREx channels.
Okay.
Then you use another set of SPHEREx channels to calculate the distance and the environment of a very distant galaxy, and you identify a similar chemical process occurring billions of years ago. SPHEREx bridges these vast differences in time and space with its systematic spectral coverage.
The fact that they are collecting 102 data points for every single object, that's what moves this from a survey to a catalog of spectroscopic fingerprints. Every major cosmic structure now has a chemical and distance profile that is publicly available.
And that access is transformative. It means that small universities or even highly motivated citizen scientists with powerful computing capabilities can contribute meaningfully to core cosmological research. The barrier to entry for analyzing the universe's large-scale structure has been lowered significantly.
The precision they must maintain to complete those 4 systematic scans over 2 years is also just mind-boggling.
Yeah.
They have to ensure that when they layer that 4th scan onto the first, they are aligned perfectly down to the pixel to maximize that sensitivity gain.
Oh, absolutely. That requires continuous, precise monitoring of the spacecraft's orientation and highly stable operational temperatures for the detectors. Any fluctuation in temperature could throw off the infrared measurements, rendering the spectral data inaccurate. The engineering feat that's supporting the science is immense.
So what does this all mean then? Let's summarize the core contribution of SPHEREx. It's providing 102 detailed spectral maps, 102 different windows into invisible light of the entire sky. And it repeats this 4 times in 2 years, boosting its sensitivity.
This multi-channel spectral data enables the first truly comprehensive, high-fidelity 3D map of hundreds of millions of galaxies. It's moving us beyond the 2D position maps and, the simple estimates of distance we've primarily relied on.
And this data is purpose-built to tackle the biggest mysteries in the history of the universe. from tracing the subtle statistical patterns, that fossil field left by the rapid expansion of cosmic inflation to the very first fraction of a second.
All the way to the continuous evolution of galaxies over 14 billion years.
Down to precisely mapping the dust clouds and ices that form stars and planets in our own Milky Way.
So you now have the context for why this particular mission, with its specific combination of a wide field of view and 102 specific spectral channels, is so essential for piecing together the universe's full history. It fills that crucial gap between broad, low-resolution surveys and extremely high-resolution, narrow-focused deep-field studies. It really is the crucial middle layer of modern astrophysics.
But the truly provocative thought, the thing for you to mull over, it comes back to the public availability of this data. If the universe's history is encoded in these 102 infrared maps, and if astronomers are using the 3D clustering data to figure out what happened during inflation, imagine this. The entire data set is freely available to the public, ready for analysis. If you, the curious learner, had access to this incredible 3D atlas focused on those 102 spectral bands, what specific structure or pattern would you look for first?
And think about that mantis shrimp analogy one final time. Even with 102 spectral channels, we are only sampling the continuous infrared spectrum. There are still structures, processes, or even entirely new molecules out there that may emit their unique fingerprint between the bands that SPHEREx is measuring, perhaps existing at wavelengths we simply weren't looking for. What key cosmic information are we still blind to, even with the most colorful, high-volume cosmic map ever created? That's the challenge that remains, even with this phenomenal achievement now in the public domain.